This video outlines a chronological blueprint for securing the Retrieval-Augmented Generation, or RAG, architecture. We will defend the AI pipeline from the initial data ingestion through to the final generation. AI security is fundamentally a data flow problem, requiring a shift from reactive front-end filters to proactive back-end corpus security. The RA trust paradox highlights a critical security flaw. User queries are explicitly untrusted, passing through security gateways. However, retrieved context from the vector database is implicitly trusted, allowing unverified documents to execute instructions within the prompt. Real-world exploits demonstrate that these attacks don't require zero-day exploits. They exploit the design assumption that retrieved text is safe. Examples include EchoLeak, Slack AI indirect injection, and SPAI-ware persistent poisoning. The threat math of corpus poisoning shows that broad compromise is unnecessary. An attacker needs only a few carefully crafted documents to manipulate AI responses with high success. Targeted semantic similarity guarantees malicious retrieval. OWASP LLM-08, 2025 identifies two major vector and embedding weaknesses. Corpus poisoning manipulates output integrity through semantic collision. Embedding inversion risks data theft by decoding stolen high-dimensional numerical vectors. We propose a three-layer defense architecture based on defense in depth. Layer 1 focuses on ingestion, Layer 2 on retrieval, and Layer 3 on generation. Neutralizing threats at Layer 1 is exponentially cheaper than catching them later in the pipeline. Layer 1, ingestion, is the priority layer. We must treat documents like code because the knowledge base is the primary attack surface. Corpus poisoning must be stopped before text is embedded, as filtering at the prompt level is too late. Hardening the ingestion pipeline involves 4 gates. These are provenance verification, format sanitization, NLP security scan, and embedding and encryption. Failure at any gate should trigger isolation, preventing downstream contamination. To defeat poisoning and inversion, we implement provenance gating to maintain an immutable audit trail. Malicious pre-processing uses classifiers to identify harmful commands. Encryption at rest treats numerical vectors as highly sensitive data. Automating checks involves integrating guardrails. Input text is checked using systems like Meta's Prompt Guard and NVIDIA's NEMO guardrails to scan for instruction semantics and block known jailbreak signatures before passing to the embedding model. Layer 2 focuses on secure retrieval and KPI monitoring. We monitor for retrieval frequency anomalies, chunk entropy variance, and anomalous bulk reads, which can indicate targeted poisoning or embedding inversion attempts. We must also enforce multi-tenant isolation. Layer 3 handles generation and output defense. Context injection detection scans the assembled prompt for malicious instructions, spotlighting and data marking explicitly separate valid instructions from untrusted RAG context. Egress output monitoring strips unauthorized URLs and blocks sensitive data exfiltration. This developer validation checklist summarizes key requirements. External documents must be tagged, harmful encoding tricks stripped, and prompt guard scanning active. Embeddings must be encrypted, and the vector database must enforce strict access control via metadata filtering. In synthesis, the unified secure RAG blueprint involves 3 phases: secure ingestion pipeline, permission-aware retrieval, and guardrail generation. The weakness is not the model, but what you feed it. Securing AI begins below the model layer.
Thanks for watching. Subscribe to Naveen Tech Hub for practical AI.